So, hello and welcome to the module we are discussing, that is on verification. In the last class basically we had in lecture 1 we had basically discussed on very brief, and we have tried to compact everything regarding LTL and CTL based verification, and mainly we emphasized how model checking is done using CTL. So, what was the basic idea we tried to recapitulate in that class, where we are trying to basically have which was mainly required for the prerequisite, that is to understand basic model checking before we can go to optimization techniques for verification. So, what we had seen in that lecture basically, that we have to have a formal model, that is a state based model for the system you want to verify, and then there will be some LTL or CTL formulas which will be basically your design intent. That means, for example, if you have seen that if you switch on the heater or the microwave, after some time it should start heating. So, some of the basic design intents, safety properties, etc., we write in terms of various temporal logic formulas, and then there are automatic model checking algorithms which will verify mathematically that whether the formula is valid in the model or not. So, if it is a very high probability or almost is mathematically guaranteed that you will get a answer yes in the model checking if both the models and the formula are correct. So, in case there is certain deviation, that either you have written a wrong formula or the modeling or the system has an error, that is why the model is not capturing what you want to implement, that is the model being or the system being implemented is not correct as per the design intent, then the model checker will tell you an error. Also, it will generate the states and the traces which is leading to the error, so that you can go and debug and find out the issues. But then what are the main complexity we have found out? In fact, that lecture we have found is quite mathematically sound, and it is mathematically guaranteed that if the formula and the model is correct, then there is no error, all the states will be model checked, and it will be told that the formula holds in all the states. Then you can be 100% sure that the model will work as per the specification. Then there is no need for any kind of simulation, because the design is correct by mathematical verification. But where the problem lies? The problem lies in the modeling itself, because when you analyze the complexity, if you recall, we found out that the main problem arises because of the model size, because the complexity of model checking is linear, it's not exponential, it's much lower compared to the size of the model, that it is basically depending on the order of the size of the formula length, that whatever is the number of different atomic propositions or the different type of formulas which you have to verify. So, the complexity depends only on the length of the formula, because for each of the formula subparts, basically like always, in future, something implies, etc., for each part of the formula you have to label certain states, and labeling certain states is nothing but it's simply a graph traversal. So, that part is not very highly complex. So, where the complexity basically arises is how you model it, because if there are 5 variables in the system, the number of states can be 2 to the power 5. Because already we have seen that the elaborate example of this microwave controller, and in which case we have only 4 or 5 variables, and the number of states were some 6 or 7. So, think of a practical system where the number of variables can be 20, and the order of states is 2 to the power 20. So, what actually kills the whole idea of verification is the complexity of the model, because that is exponential in the number of variables, and in most of the cases a practical system will have hundreds of variables. So, that is where the crux of complexity comes in, where we require optimization. Now, throughout this lecture we will be trying to deal with those complexities. Right, the next 2 lecture set will be verification of large systems, where first we will see about binary decision diagram based verification, and then we will see arithmetic decision diagram, high level decision diagram based verifications. In what case basically BDD is a binary decision diagram which is nothing but a very nice data structure. One of the data structure, most beautiful data structure I have ever seen, which has revolutionized the whole CAD industry, that it has shown how a simple binary tree can be compacted and all redundancy can be removed, and we can get a very nice data structure which is very compact. Actually, when I say, this is, you should all have a feeling, whenever we say that the number of states is order of 2 to the power 20, order of 2 to the power 30, if there are 30 variables, it is not actually order of 2 to the power 30, its order is 2 to the power 30, but the real number of states there is much lower than that, because all combinations cannot happen, because among all the variables there are only very few meaningful combinations which are actually required to model, all other are very much redundant and can be eliminated. But if you are using a very rudimentary binary tree type of data structures or a simple finite state machine based structure, then all the states will be explicitly enumerated, leading to the higher exponential complexities, making the modeling itself so complex that verification cannot go beyond a toy example. So, if you look at most of the literature, very few of them handle even a system which is as complex as a braking system. It will be, most of the works basically try to deal with very small system having 10 to 20 variables. About systems handling about 50 variables are very rare, and you only find in very specific cases in generally if you look at the paper and the literature. So, compared to testing, VLSI compared to testing, verification is a more difficult problem in terms of complexity, because testing inherently is not exponential. Inherently it is such kind of searches, because we do not require an explicit modeling of the system in terms of states and transitions. But in case of verification, it is the other way around. We always have to start with the modeling of the states, and a state transition diagram is required. So, whenever we talk about state transition diagram or a graph, exponentiality actually kills us. So, what we will see, in this 2 lecture series, we will see basically a data structure called BDD, which will try to compact the representation, and then we will see that BDD is again a binary representation. Can we go for some abstraction like arithmetic or high level decision diagram, and then we will move ahead. So, basically we will start that throughout whenever from computer sciences come into picture, we know about the Boolean function, binary arithmetic, that zeros and ones. So, basically whenever you want to represent anything, you have a tree which is a binary decision tree, is a very well known data structure. So, the internal nodes are the variables of the function, and then there are trees with leaf nodes zeros and ones, and each internal node has 2 child. Basically you all know that. So, there will be a variable say x, and this will be for 0 and this will be for the 1 variable. So, here we actually represent by the dashed line. So, whenever we will be representing the 0 for 0 variable, if x is equal to 0, we generally take the left edge, and if x equal to 1, we go the right edge, standard data structure. But in this course and most other CAD courses, you will find out that they actually make a dotted line for easy illustration, and only problem is that actually you will blow up. That is the only thing. Otherwise, binary decision binary decision tree can actually represent any kind of digital systems. Only problem is that the exponential blow up. Idea is very simple. You take the variables, left child 0, right child 1, and all the possibilities you enumerate, and finally the leaf node will have the values of zeros and ones. If you take a path from the root node to the leaf node, you will find out that what is the value of the function if those variable values are taken by the path traversed from the root node to the leaf node, standard data structure algorithms. Basically, how do we represent circuits? Generally, the most important one we study in our digital design is a truth table. So, we have all inputs, and basically we have all outputs in a part of the table, that one side will be all inputs and one side will be all outputs. And basically how many rows will be there in the truth table? If there are n variables, there will be 2 to the power n rows, 0 0 0 0 0 1 dot 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 up to 1 1 1. All the inputs will be explicitly enumerated, and for each of the inputs what will be the outputs? We are assuming m outputs, so that also has to be enumerated. So, what will be the size of the table? The size of the table will be easily equal to 2 to the power n for all the rows and into m, because that many number of columns will be there. So, it is some order of like this will be basically size, that is we will have this many rows, and basically columns also basically I am saying it should not be m is the output, n is the input. So, basically your table would look like something like this. So, you have 1 2 dot 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 2 to the power n, these are all the values, and this is O1, this is O2, all the outputs will be enumerated up to m outputs. So, generally they say that there will be 2 to the power n rows and 2 to the power and m columns. So, basically that is what is the size of a truth table. So, basically it is nothing but you explicitly enumerate all the inputs and outputs. So, that is the most fundamental and easiest way of representing a circuit. Then basically the truth table can be easily converted into a binary decision tree. Like for example, this is an simple circuit if you can look at. So, the output function is AB plus CD. Let me just zoom it for you. So, this is a simple circuit, AB plus CD, and this is the function AB plus CD. Now, if I want to represent it in terms of a truth table, so you will have AB, CD. So, we will start from all zeros to all ones, and there is only one output. So, it will be O1, and you can write out the values over here for all the rows explicitly. So, this is actually the truth table representation. Simply it can be represented also as a binary tree. There is a standard data structure. So, we will have the first variable, that is A, the second will be B, so all these will be, third will be C, as you can see this is the third variable in the sequence is 3, and fourth is D, and explicitly enumerate. You say that if A is equal to 0, I go this side, if A equal to 1, I go this side. Then basically, so if A equal to 0, I go this side. Then if B equal to 0, I go this side, if B equal to 1, I go this side. Similarly for this and similarly for D. Basically all the paths you explicitly enumerate in terms of a tree, standard decision tree is there, and you get the values. Like for example, if A equal to 0, B equal to 0, C equal to 0, D equal to 0, the output is basically equal to 0. So, for that you have to actually look at this part of the tree. If you can look at, so A equal to 0, B equal to 0, C equal to 0, D equal to 0. So, this leaf node is marked with a 0. Similarly, you have to enumerate for all the cases. If you count 1, 2, 3, 4 in the leaf node, you will be 16 leaf nodes for that. Basically, but if you have the values of 1, 1, 1 and 1, the output will be 1. So, 1, 1, 1, 1, if I put, the output will be 1. So, basically 1, 1, 1 and 1, the output will be 1. So, for all the individual values, for all the, these are actually these leaf nodes are all the output, all the row correspond to all the rows of the truth table. And if you take one path from the root node and if you come to any of the leaf node, this corresponds to one entry in the truth table. So, this is basically nothing but a graphical representation of the basically your truth table. So, very nice graph, you can do lot of reasoning, and you know that if the number of inputs are n, the number of leaf nodes will be 2 to the power n, and all the nodes in the non-leaf nodes will be equal to 2 to the power n minus 1 standard data structure. These are basically the orders. So, if you have 100 input circuits, in fact, we will practically cannot even draw the tree. Even if it for a 15 input circuit, such trees cannot be drawn. So, that is where actually the complexity comes. Now, why I am talking about all these basically this binary decision tree etc. when you are talking of verification, basically whenever it is a system, basically there are flip flops, and then we have state variables and state enumeration, which is mandatory for verification. But state, I mean, if you can recollect your sequential circuit design fundamentals, we always have basically a combinational logic, which is the next state function block, and then we have a flip flop. So, and then we have a flip flop. So, we actually try to model the whole finite state machine in terms of next state logic, that is your flops. Sorry, we have something like this. If you take something like this, is your basically your flip flops, the register bank, then you have an input. This is your combinational cloud, that is your next state logic block, and there are feedbacks from here, and also there are primary inputs. So, this is basically your nothing but your combinational circuit. So, if you have some good data structures to model this combinational cloud, modeling the flip flops is nothing but just enumerating the state values. We will have an explicit lecture to see how actually binary decision diagrams can be used to represent models, the state space model, which is the most difficult part in verification. So, first we are trying to see how to model this NSF block, that is a combinational circuit, using some good data structure. Once we can model this, modeling the state variables is trivial, because there is just flip flops means just take the value from one state to the next state. This is just a straight transition. That modeling is not difficult if we can have a good data structure to model the NSF block, that is the next state functional block, which is a combinational circuit. So, that is why we are mainly dealing with combinational circuits here when we are explaining binary decision diagrams. Because for the time being, we just assume that if I can model the combinational circuit in a very nice and efficient manner, we can handle the complexity there, then modeling of the flip flops will be trivial, right. So, the problem here is that I have told you, so that basically the n input rows and m output rows, the order is 2 to the power into m, basically that is the truth table. And for the binary decision diagrams, basically one thing you have to know that one binary decision tree will be for one output. If there is another output here, maybe then another gate will be there, another output will be there. As many outputs will be there, that many binary trees has to be there, because one binary tree represents one output. So, basically the order will be 2 to the power n minus 1 plus 2 to the power n, that is the leaf nodes, non-leaf nodes into m. Why n? Because there are m explicit trees required for m outputs. So, huge complexity. So, obviously nobody can even think about modeling a practical system in terms of a binary decision tree. Basically then something actually which revolutionized, it was by Bryant, R.E. Bryant. So, we are all thankful to Professor Bryant for finding out such an interesting data structure, which actually revolutionized the whole CAD industry. So, binary decision tree cannot be generated in practical timelines for a reasonably complex circuit. Reasonably complex here means even in 20 it is very difficult. The main reason is the exponential number of nodes in a binary decision tree. Now, what Professor Bryant observed, that there are a lot of redundancies. We have to start eliminating the redundancy. Even if a child can tell that, if you look at, even a child can tell you where are the redundancies. So, even a class, junior school student can tell you there are so many redundancies in the leaf node, because leaf nodes can have only two values, or 0 or 1. But redundancy means if there is 1, 2, 3, 4, 5, if you count, there will be around say 50% of zeros and maybe another 50% of 1s. That means basically in this case maybe sometimes we will have 25% 1 or 25% 0 or some numbers. But actually, if you can find out that very simple is that I can write only 1 0 and only 1 1. Only 2 nodes I will have, and I will make a redirection for everything. This one I will put it over here, because straightforward I can see there are a lot of redundancy in the leaf node. So, I eliminate all, I just keep 2 of them and redirect the edges like that. 50% is 2 to the power n minus n, that is the last node complexity will be gone in just a click. So, but very interestingly, before Professor Bryant, nobody could think about it. People were just thinking about handling complexity in different manners by abstraction, etc. But this practical feature, on this practical observation was one of the key observations which actually found out will lead to the direction of the development of this data structure called binary decision diagrams. Quite interesting. But just like as you have seen, as I told you, like scan chains and many other fundamental data structures or fundamental algorithms in the VLSI design test verification are based on very, very simple observations. Like in this case, there are so many redundancies in the leaf node, eliminate the redundancy, just put 1 0 and 1 node, because in case of binary, when we are talking binary system, there can be only 2 outputs, 0 and 1. So, throw away all repetitive zeros, put only 1 0 and 1 1 block and redirect, your job is done. But then that is only one part of the story. Now, people have found out that not only in the leaf node, in the non-leaf nodes also there are a lot of redundancies, we have to try to eliminate them. Now, that is what is basically something called a binary decision diagram. So, this 0 and 1 can be redirected accordingly. Similarly, this reduction is carried out at all layers till the root. That is what is binary decision diagrams. You reduce the leaf node, done. If you find similar type of redundancies, you go to the top and keep on doing it. We will take examples and find. So, binary decision diagram is a directed acyclic graph, Boolean expressions which cannot be further reduced by redundant nodes. So, redundancy means if you can throw away that node and do some kind of redirection, the Boolean function does not get changed. So, therefore, sometimes BDD people better actually call it reduced BDD or BDDs basically. So, basically BDD whenever talk you, sometimes this reduced term is no longer used directly, but it means that the BDD is in reduced form, because it cannot be further reduced. Whatever extra or redundant variables or all these duplicate stuffs are there are all been eliminated. Then it becomes a binary decision diagram. And surprisingly, the compression or and as I told you, this is one case of optimization where there is no loss in quality. That means you have a very big data structure, a very big tree, you eliminate the redundancy and you get a smaller size tree. That is the binary decision diagram or reduced binary decision diagram. But interestingly, the function does not change. Means for whatever sets of zeros and ones for the inputs which will give 1, the same case will happen in binary decision tree as well as for the binary decision diagram. That is, for any input you take, any input combination you take, both the trees will give, both the decision trees, BDD or binary decision tree will give the same answer. That is, you are not modifying the function, only we are eliminating the redundancies. So, this is one very good idea, fundamental of BDD is that it compresses, but still without any loss, or that is without any compromise it goes for an optimization. And surprisingly, the reduction for most of the cases is 99 plus. Maybe in a BDD, a binary decision tree, you have say 10 million or 1000 nodes. If you go for a binary decision diagram, for most of the cases it may come to around 10 or 20 nodes. Reduction is 99 plus. Only for very few cases like a multiplier algorithm etc., there is no big reduction, but those type of functions are very, very less. In most of the general purpose circuits or general purpose systems, the reduction is drastic. That is why I always say that BDD is one of the best data structures I have ever seen, which has revolutionized the whole CAD industry, because all the algorithms now written in CAD is in terms of BDD. After that we had several advances like arithmetic decision diagram, high level decision diagram, but the basic fundamental is this: remove all the redundancies and try to compress as much as possible. So, basically simple 3 rules will revolutionize. One is called the removing R1, which is called the removing of the duplicate leaf nodes. That is very simple. All zeros and ones you remove, put only 1 0 and only 1 and redirect the paths accordingly. R2 is actually called removal of duplicate non-terminal internal nodes. That is basically away from, not from the leaf, above the leaf, if there is some redundancy is removed. How you do it? If any 2 distinct nodes M and N say are the roots of structurally identical sub BDDs. That means say this is one root and this is one root. So, the BDD here and this say BDD here are identical. Then basically say maybe there is some from path it is coming and from there some other path it is coming. The BDD here and the BDD here are similar. Then what you can do? Similarly, you can delete this N and redirect this path to N. That is what is the elimination of redundancy from the higher level. That is same philosophy. BDD is actually obtained from binary decision tree by reducing or eliminating redundancies. Leaf node you do, R2 is that if you find out some internal nodes or internal sub part of the tree is looking similar, remove one sub part and try to merge the edges such that only one common sub part is retained and the other is removed. And basically finally R3 is removal of redundant test. Basically if both outgoing edges of node n point to the same m, then remove n. It is very simple, like this is one node called n and they both point to n, that is this one. Both 0 and 1, if the value of variable n is both 0 and 1 leading to the node called m, then you can eliminate n. That means n whether 0 or 1 is leading to the same child, then basically n is not required. In case of binary decision tree, what we will do? You will write n 0, sorry, for n equal to 0 maybe it is going to some value and basically maybe 0 and n equal to 1 also may be going to same value. So, in binary decision tree what you write? You have to do in this way, n equal to 0 to 0, n equal to 1 to 1, assuming that basically it is some kind of a leaf node. So, it is you write in a binary decision tree. But in binary decision diagram, if it says that in any node, if it points out, sorry over here, what I was trying to say, basically in case of binary decision tree, if n equal to 1 you get 0, n equal to 0 equal to 0 and if n equal to 1 equal to also 0, then we write it in this way. But actually this is very much redundant. So, the rule tells that not only about the leaf node, at any point of time if you find out that n both 0 and 1 is leading to the same node, because in case of binary decision diagram we will have a single node, you have to just eliminate n and this. So, it will become. So, in binary tree we do not think of any redundancies, we just keep on putting both the conditions left child, right child, left child, right child and we blow up. But here we apply these 3 rules, leaf nodes we all eliminate, keep only 2, redirect. Internally we search that if there is 2 common sub BDDs, then retain one of them, other one you eliminate, redirect the edges accordingly. And third is basically if you find any node where both the edges outgoing left child and right child is going to the same other successor node, then removing the parent node and redirect accordingly. So, Bryant there are a lot of mathematical proofs behind this which I am not going. So, they have proved that by using these 3 rules till you get the minimal structure, basically will give you the reduced binary decision diagram, and you cannot have any further reduction beyond that. That means that is the most compact representation of the function, you cannot have any more reduction. By applying these 3 rules, or these 3 rules are enough to, if you take a binary tree and if you apply these rules, ultimately you are going to find out the best solution from which you cannot further reduce. Therefore, it is actually called the basically called the reduced binary decision diagram. We will start taking an example. So, I am not going to go hence and forth, basically this is this tree, means I will just remove all the figures for you. Anyway, all the written notes for this course will also be uploaded in the website. So, this is the binary tree. Now, I eliminate all these leaf nodes and I keep only 2 of them. So, if you look at it, I will get something like this, because I have only 2 nodes for 0 and 1. So, all the duplicate nodes have been removed and I get a path like this, tree structure like this, only one edge we will study. So, it will be easier for you. Let us try to concentrate on this part. So, C, D all 0 leads to 0, C equal to 0, D equal to 1 leads to 0. So, basically we will see how it is getting reflected. Okay, the left part C0, D0, 0, C0, D1 also 0, that is this part. So, we will see how it is getting reflected in the binary decision diagram. So, if you look at it, this part let us zoom. So, if you can see C equal to 0, D equal to 0 is 0. C equal to 0, D equal to 1 is also 0. So, in the binary tree we basically had something like this would not have been there, you would have another node which is 0, basically this is the dotted line. So, basically we will say that C equal to 0, D equal to 0 is 0, C equal to 0, D equal to 1 is also equal to 0. So, unnecessarily we had one replication. So, now we have in this case of binary decision diagram, by applying rule 1 we will actually make both the edges point to a single node, because we have only 1 0 and only 1 1. So, now you can easily look at this tree and all the you just draw this, basically eliminate all the root nodes, have only 2 nodes and redirect the edges I have shown for one example, this tree will be obtained. So, straight away first reduction is coming down from 2 to the power n to 2, basically the leaf node there was 2 to the power n child. In this case it was 1, 2, 3, 4, that is basically it was 4, 16, from 16 to 2. So, the root nodes, number of root nodes of a binary decision diagram will always be constant, that is equal to 2 or less. Sometimes it can also be less, that we are going to see, because if the function always gives 0 or always gives 1, there will be a single node, but it can never be higher than 2, that is what is the beauty. Now interesting parts we are going to do, that is R1. Now as I told you, we will try to find out common subgraphs in this. So if you look at, let us try to look at this subgraph. So what the subgraph is saying, let me try to zoom this subgraph. So if you look at this subgraph, it says that C equal to 0, D equal to 0, sorry, C equal to 0, C equal to 0 is 0, C equal to 0, D equal to 0 is this one, C equal to 1, D equal to 0 is 0, C equal to 1, D equal to 1 is 1. So this is one graph. Let us now look at this subgraph. So another subgraph basically, if we consider, let me eliminate this and take the other subgraph. So just let me take this subgraph, okay, and you see again C equal to 0, D equal to 0 is 0, C equal to 0, D equal to 1 is this, C equal to 1, D equal to 0 is 0 and this. So if you look at it, these two subgraphs exactly look similar. C0, this edge, this D node and this D node is similar. Similarly, this D node and this D node is similar, because 0 means 0, here also 0 means 0, here also 1 means 1, D equal to 1 is 1. So these are the two, there may be more. I am just taking because I think this part also will anyway. So there are similar other subgraphs which are common. These 1, 2 subgraphs or sub BDDs which are common in, which are redundant, because they are exactly common. So basically one of them can be easily eliminated. This part can be eliminated. Of course the leaf node you have to keep basically. So this part I think can be very easily dropped out, because they are very similar. You just keep one of them and readjust accordingly. That means if you eliminate this B only has to be redirected over here. Your job is basically done. Why I want to keep redundant variables. Similarly, if you look at this part, C, D, D, this part of the tree if you take, anyway let me eliminate the other part. So you can see in these two parts, let me study. Okay, so if you see C, if you look at, sorry, not this B, I will just drop this, not this one, on this part if you see. So this is C equal to 0, D equal to 0, so C, D same path, C equal to 1, then D. So no, this is not common basically, because in this case these two nodes are not common, because in this case both of the D's are leading to 1, here the D is different. So these two are not subcommon, but basically you have to find out all such kind of common subgraphs in the tree and eliminating them. So basically these two are not common, but because this D and these D nodes are not equivalent. So therefore these two are not common, but this subgraph and these subgraphs are sub-BDDs are common. So basically what is being showed in this, a pair of duplicate sub-BDDs enclosed by the polygons. This one you can just I will just zoom it for you, quick view. So this part and this part are basically common, similar. So what we do? We eliminate it. So if you eliminate, what is going to happen? There will be only one such subgraph, and basically this B will start pointing to C. If you look at it, so this is what has happened. So this is your basically the graph. So this is your graph, sorry. So basically this is your graph, C equal to 0, D equal to 0 and 1 similar, C equal to 1, D equal to 0, 0 and 1. So if you look at it, this is this graph. So this is the path, and in this case C, D, C equal to 1, D equal to 0 is 0, D equal to 1 is equal to 1. So basically this is the path I was talking about, and this part. So this part is what is remaining, and as I told you, you have to also adjust, because if one of them gets eliminated, the left child of B will also have to start pointing to this edge. So basically this is gone, B will, this part of the B will also start pointing to this C. So basically these are what has happened. This is your common, sorry. So basically this is the graph, which is one part we have retained, the other part we have deleted, and this part of the D, that is the dotted line which is pointing to the subgraph that is eliminated, will now start pointing over here. Similarly, you have to, if you search the whole graph, there are a lot of such redundant trees, and you will find out something, some intermediate binary decision tree which has no redundant subparts. So I am not going for all these steps, very easily you can try to look out in this graph, find out the redundant one and is eliminated. Basically you can find out, maybe there is some kind of duplicacies over here. So anyway, that you can study and find out. Now basically what? Now other rules you have to write, like for example, very simple, you can see that these nodes are basically not required. Very trivially you can see, because both the left edge and right edge are going to same thing. That means I don't care. Basically in terms of detail, they are don't cares basically. B equal to 0, C equal to B equal to 0, B equal to 1. Basically you are going to same C. In fact, I don't require this at all. I can directly bring my A dotted line here. Similarly, this D is also not required, you can actually directly bring this down over here, this can be eliminated. Similarly, this D and this whole stuff is not required, you can directly bring down this one over here, because these nodes are not required, because whenever you have both zeros and ones leading to this, so they will do the same thing. So basically you will have something like this part will be eliminated, this part is also not required, you will bring it to here, this whole part is not required, directly you can bring it up to here. So it will actually somehow lead to some graph like this, which is the most reduced form. You cannot, for that given function, you cannot have any further reduction than this. So how many? From 16, that is 2 to the power 4, 2 to the power 4 plus 2 to the power 3, basically 8 plus 60, that is something around 30 nodes, we have brought it down to 1, 2, 3, 4, 5, 6. So from 6 from the order of 30s, so 1/5 reduction. Basically this ratio will actually again blow up, means this size will start exponentially rising, and this rise is basically linear if you are going for a large functions, like if you have some functions like 100 variables. So this will be in the order of 2 to the power 100, but this one will not increase in that order for general most of the functions. It will be around some 300, 400 or maybe 1000 or 10,000 nodes. So basically the size of the BDD on the number of inputs do not blow up exponentially for most of the functions or most of the cases, but the denominator, which is a binary tree or a exponential function, actually blows up. Therefore the ratio of compaction is very high when you are using a binary decision diagram, as the example shows. And the most beauty of it is that this function and the original BDD functions are not changed. So whenever, like on one example we had seen that if A equal to B 0, B equal to 0, C equal to 0, D equal to 0, you are getting the value of 0. In this case, if A equal to 0, C equal to 0 is 0. That means D equal to 0 and B equal to 0 are redundant variables. That means they are basically don't cares. So very quickly you are going to get the solution, and that also without any error. Like we already see that A equal to B equal to C equal to D equal to, if all zeros, the answer was a 0. So just you have to traverse the BDD, A equal to 0, B is redundant, so you will not find B over here, C is 0, D is not required, you find the answer 0, so it is correct. Basically BDD are also one thing, if there are some redundant variables in paths, they will all be eliminated, but B is not redundant in this path, so it is there. But if some of the variables are totally redundant, they are not required in the function, which can be minimized, which we do in terms of Karnaugh map, etc. BDD will totally eliminate those variables from the tree, you will not find them in the tree. And from the this path example I have shown you that A equal to 0, B equal to 0, C 0, D 0, like this one, like this example, this path like A, B, C, D, this path, actually in this path A and B and D are redundant, so you can directly have this. So what is saying is that whatever output the binary tree will give you, binary decision tree will give you, the same input will be given by the binary decision diagram. So they are basically equivalent, but this is very compressed version of the binary decision tree, and the compression happens because we are eliminating out all the redundant nodes. First you are eliminating all the leaf redundancies, then you are eliminating all the intermediate redundancies, then you are finding out some edge nodes where basically both zeros and ones are leading to the same child, and we are trying to eliminate out those nodes and redirecting the transitions accordingly. So you are getting a very complex structure. That is what is the beauty of binary decision diagrams. So what it means, that if you have a very big circuit in terms of hundreds of inputs, the binary decision diagram will be much smaller than the binary tree, and this binary decision diagram will be used to represent basically your state machines, and all the model checking we have done in the state machine labeling will all be done in terms of binary decision diagrams only. So the modeling structure will drastically change from explicit states to BDD based representation, and the model checking of state labeling, etc. will be done not only on the explicit state machine, it will be done symbolically on the BDD. So that will actually improve the scalability or the complexity in a drastic fashion. So what is the step? On one side we have a state machine, which is the exponential, then we have some temporal formulas like CTL, LTL, we do a model checking on the graph. That is actually a very complex problem if the number of state variables are large. Other side is that we will not even go for the state modeling, we will directly represent the state variables or the finite state machine in terms of BDDs, and as already shown in this case, it will be extremely compact representation of the whole state enumeration. Then you can have very big circuits or very big systems represented symbolically in terms of BDD, and you did not explicitly represent them in terms of the state based modeling. Then what do you do? then all the model checking algorithms like labeling etc. will not be done on the explicit state based machine, but it will be done on the BDDs, resulting in more efficiency in those algorithms, and very quickly you are going to get out the solution. So, using of BDDs will help to verify very large systems by representing them symbolically. The term symbolically is used when you are using verification everything or representation in terms of decision diagrams, binary decision diagram. Now, one important thing we are going to study, that is construction of BDDs. So, now what we have seen in the last example, that we have a binary tree and then you are making into a BDD. So, it should always come to your mind that if you have the binary decision diagram or binary decision tree, then we are using lot of elimination etc. to do it. But the binary decision tree itself is not available for a very large circuit. Then how can you make the binary decision diagram? Because you have a very big structure, you are reducing and you are making a binary decision diagram. But how to make the big tree itself, that is a very big question. The idea is that nobody actually does in that fashion. This was shown to explain you the difference between a BDD and a binary decision tree. Basically, people try to build binary decision diagram from the scratch. That is, they will have some very small trees, they will merge them and try to make up a bigger binary decision tree. Because that is impossible, that you have a binary decision diagram, very big one, and you start reducing and making a tree. That is not possible. Binary decision diagrams are basically built up from atomic gates, and they will make the larger binary decision diagrams. That we are going to show. Basically, when Bryant etc. tried to compress, at that time there was no binary decision diagram. They were looking at binary decision tree and they were trying to find out that there can be a data structure which will compress it in this manner. So, therefore, this was a thought process and to illustrate the beauty of binary decision diagram. But practically, when you are going to construct, nobody can construct it in the fashion which you have seen, that you take a binary decision tree and then you reduce and make it, because binary tree itself is not available. So, what actually we do? We actually construct reduced BDDs using something called a Shannon's expression. So, as I have told you, the binary decision tree is a very small structure. Time taking to make a BDD is prohibitive. So, to obtain BDD, we need not start with binary decision tree. We need not is not a good word. We cannot start with a binary decision tree. Our BDDs can be directly generated without a binary decision tree. Basically, for that we require something called Shannon's expression, in which case whenever you have a function called f of x, we will have two paths, one x is equal to 0, then x equal to 1, then this will be one BDD. Then again we will keep on doing it till we get the finally binary decision diagram. And at every stage of the construction you have to keep on reducing. You cannot have the whole exponential growth and then reduce, that is not possible. You take a function, make a binary decision diagram or make a binary decision tree rather, eliminate redundancies, make it a binary decision diagram and then go for the next level of combinations, which is actually that is growing the binary decision diagrams from the leaf levels. For example, what we do, if we have a function called f of x, generally Shannon expression means we have one part in which f of x equal x dot x equal to 1. That means if you have a function which we first take out one variable, replace that variable by 1 and make a sub function inside, then another part is x equal to 0 and the other part is replaced by value of x equal to 0, we get another function and we keep on doing it. Basically, easy to this is actually mathematical representation, very easy to explain by an example like this function ab plus bc plus ab. So, what we do? First we say that a equal to 1, if a equal to 1 means you replace the value of a equal to 1 and a equal to 1. So, you are going to get 1 dot c, b dot c, 1 dot b, that is actually f of a replaced with 1, that is nothing but equal to b plus c plus bc. Now, second will be I will replace a with 0. So, if you replace all a with 0, so this term will go, this term will go, only bc will remain. So, this is nothing but equal to f this one. So, finally, we can write this one as f of function a is basically nothing but a, correct, into b plus c plus bc and is a bar, that is a dot is equal to bc. So, now again we have to do it in terms of b, do it in terms of c. Basically, that means the first node is a. So, a0 will be equal to bc and a equal to 1 is nothing but equal to the bigger one, that is equal to b plus c plus bc, and you have to keep on doing it and every stage you have to keep on reducing. That is what is the idea of a binary decision diagram construction using Shannon's expression. Because even for a very big circuit or whatever, you have at least the function. Function is nothing but your design intent. That is a very compact representation. Whenever we want to convert these functions to some kind of models where we can do model checking on algorithmic verification, then we require a graphical or we require a data structure which can represent it from all the paths, traversals, etc. Because function is nothing but some ab plus bc plus c, some variable combinations. We cannot do much with it. But to go for logical reasoning, all these things we should have represented in terms of a decision tree. So if you make a binary addition tree, it will be very large, but with Shannon's expression we can construct BDD from the basic root level itself, so that we can get a compressed structure at every stage. So basically how we start about it. So basically maybe we have a function called, first we start with a preliminary function. Maybe we have some variable called x. So first we will have the two leaf nodes. Whenever we try to build a BDD, we start from the leaf. So there will be only two leaves, as we know, 0 and 1. Then maybe there is one variable. For all variables you have to make a structure like this. x0 is 0, x1 is 1. That is the variable itself. I assume that is only my input. So if you have input x1, x2, x3, x4, x5, so you will have this for the root, this will have it only once, and how many variables you have, you will all have trees of this nature. That is, x is 0 means 0, x is 1 is 1. That is representation of x. Now we will merge them and try to make larger BDDs. So those things actually we cannot cover in one class, but we will cover in the next class. We will see how to make such bigger BDDs from smaller BDDs. But what Shannon expression does, it takes first the leaf nodes, then all the variables it is enumerating, because it is very easy to understand that if I want to enumerate x, a single variable in BDD, so x0 is 0, x1 is equal to 1, that is the value of x itself. So all these leaf level stuff they will make to leaf level, and all the variables they will make, and then they will try to merge them and make a bigger model, but at every step they will reduce. So that is actually BDD construction, which we will see in details later. So basically if you say they represent in some manner, so if you have a bigger function, so we will have f of a over here, and then we will have this sub function of Shannon, that is f a. In that function all a's will be replaced with 0, and what is the value we will have, and this part will actually have all the a's which are replaced by 1, and this one actually you will have to merge them to make up a larger binary addition diagram. We will take all examples, do not worry about it, just the theory I am telling you at present. So basically we will start from something like this. This is the function AC plus BC plus AB. So what we are going to have, they are taking A as the leaf node, because they are assuming that the level of A is first, then the next level of node will be B, then the next ordering will be C, and so forth. So A equal to 0 means we have already seen the value of BC. So let me zoom in. So we are having something like A equal B, this was the function AB plus BC plus AB, and then AB, this is the BDD, Shannon's intermediate representation. So BC and then BC plus C plus BC, because if I make A equal to 1, you are going to get the value over here. Next what they are going to do, now same thing they are going to replace with B, sorry. So this will be 0 and this will be 1. So if B equal to 1, you are going to get the value of C over here, and if B equal to 0, you are going to directly get the value of 0 over. This is dotted line, this is dotted line. Similarly, you have to represent for again for this and for this. So if B equal to 1 over here, then actually it will be 1, this one will be equal to B equal to 1, that is 1 plus C plus B. So if you look at it, it is nothing but equal to 1. So I have to put a 1 over here. And if you make B equal to 0, so in this case you can find out that the answer is equal to nothing but the node C. Right, this is B plus C plus BC. If I make C equal to 0, B equal to 0, then this is gone, only C will remain. So this is the next intermediate structure. So this, So same thing is written over here, and then you have to, so only one more node remains, that C equal to 0, what happens, C equal to 1, what happens. So basically now if C equal to 0 means you are going over here, C equal to 1 means you are going over here, and this procedure basically repeats. So this is one way of forming the BDDs, and at every stage you have to eliminate the redundancies. We will take explicit examples to illustrate all these things, but I think you have got the idea that how we can go about in forming the BDDs by Shannon's expression. We have a function, we have to select the order, that A or B or C or D, and keep on explicitly enumerating A equal to 0 this, B equal to 0. Then again you have to keep on doing it till you get the fundamentals like this was the leaf node, this is the root node, and similarly you will keep on expression, and finally you are going to get the binary addition diagram, something like this. So what I had told, if you make a tree like this, as I was discussing, like again in this case it is B equal to 0 means it will be finally a 0. So B equal to 0 means it will be finally a 0. Then if B equal to 1 here means you have to go for C, and then only you can decide if B equal to 1. So if B equal to 1 means C. So basically if you look at it, B equal to 1 means it is C. So then again C will decide, and this is the leaf structure of C, as we have told you, C0 0, C1 1. So all the, if you have some leaf structures or variables in the end, leaf variables, so it will be represented by 0 and 1. That is nothing but this structure. this structure. So similarly, I mean for all others it can be expressed like A equal to 1 means, as I told you, BC. So now again this will be now becoming B. So if B equal to 1, it was nothing but equal to 1. So if you see A equal to 1, B equal to 1, you can directly go over 1. That is, it was B equal to 1 means C plus 1 plus C plus 1 plus C plus C. So this is nothing but equal to 1. So in this case C is basically becomes a redundant variable. So that is why you are writing from A, from B you can directly have a leaf node. So in this way you are going to get it. But now at every stage basically it will have some redundant node. Every part you have to, after every finally you go for at each step you have to actually go for redundancy elimination, because in this case you can see there are some redundant nodes in the left. So use the rule R1, R2 and R3. So you are going to get this final minimized version. So this is one way of generating the BDDs using a Shannon's expression, that you take a node, then you decide the ordering. So ordering is A, then B and then C. Then you take A equal to 1, have the subgraph here, have the subfunction of A equal to 1 here and B in the left side. Sorry, A equal to 0, this is the subfunction, A equal to 1, this is the case. Now you again do it for B, then do it for C and keep on doing it till you get the leaf nodes, and every time you have to see for this redundancy elimination, and finally you are going to get the BDD based function. So in this case you need not actually have to go for something called, the previously we were discussing, that you are actually taking a binary decision tree and you are going to make a BDD. So that is not a way of, explicit way of doing it. So this is a Shannon's expression, a way of making a binary decision diagram or reduced binary decision diagram from the function itself. But sometimes what it may happen is that you can have the circuit itself. By looking at the circuit, you have to make a binary decision diagram. That is another way of doing it. For that you have to know the operations of BDD. So operations of BDD is a slightly detailed topic which we will cover in the next lecture. But I think till now you have got the idea that binary decision diagram is a very compact representation, but you do not require a binary tree to do it. If you have the expression, you can use Shannon's method of doing it. At intermediate steps, you have to somehow eliminate the redundancy. Another more interesting way of doing it is that given the circuit itself, how can we do it? That also we are going to see in the next lecture. But before that, one very important part is actually the ordering. So what was the ordering? That what I have said is that first you are taking A, then you are taking B and then you are taking C. You can also have taken the other way around, that in this function I could have started with B equal to 0 and B equal to 1, and then again I could have drawn the whole tree. I could have also started with C and I have to do it. Is the size of the BDD same? Surprisingly no. Answer is, for different variable orderings the size drastically differs. So that is one bad thing I should say about BDD, because if you take an arbitrary variable ordering, the compression may not be very high. If you take a very good variable ordering, then the compression will be very good. So therefore binary decision diagrams are size of binary decision diagram is very much dependent on the ordering. And of course if you want to have some kind of finding out whether two Boolean functions are equivalent or some properties, equivalent checking, etc., the same ordering you have to follow. Because if you have a function, if you have another function, if you want to find out whether these two functions are equivalent or not, then the two BDDs will be identical. That is proved, because the number of variables will be minimum in both the cases, subject to ordering. That means for one you cannot take the ordering like ABC, and the other you cannot take the ordering as BCA. That is not possible. If you take the same ordering and if the two Boolean functions are equivalent, the same BDDs will appear, and for that given ordering there cannot be any more reduced size decision diagrams if you are applying the rule R1, R2 and R3. So that is why BDDs are also sometimes called reduced ordered binary decision diagram, because ordering is very important. Anyway it is reduced, because if you apply rule R1, R2 and R3 you cannot have further reduction. But on the same time you have to also appreciate the fact that it is very much dependent on the ordering, that what is the first level, second level, third level, fourth level, what are the variable orderings you are using for the Shannon based expression, or in any way you are generating the BDDs. In case of binary tree, whatever be the size you take, the tree will always be exponential, because everything is explicitly mentioned in the leaf node and the sub leaf nodes. So whether you take BCA or ABC, there will be no change in the structure of the circuit. Always everybody will have two nodes, each child will have two nodes, and similarly it will go forth. But in binary decision diagram, rather ordered binary decision diagram, the order actually have a great impact. So it says that RBDD represents a Boolean function similar to truth table. Binary decision, however, the number of nodes do not grow exponentially with the function. R of BDD is very suitable for represent function. That is very good. But ordering of variables in the context of input is very important, because number of nodes of a given Boolean functions depends on the ordering. That is, if you are taking a good ordering, the number of nodes in the BDD is less. If you take a bad ordering, it will be very high. How to then find out good binary ordering? There are a lot of heuristics and methods available which we can guess that which is the best or very good binary addition, good binary ordering, or variable ordering. But if you ask me that to find out the best binary or Boolean variable ordering, then that problem is also very difficult problem. Nobody tries to solve that in a very true manner, because there will be one or two or some ordering for which we will get the optimal answer or the best answer, most reduced version you are going to get. But to find out that ordering is a very difficult problem to solve and more time taking. So that will again you will lose out all the interest of using BDDs for lowering the complexity. But the good thing is that for generally for a given variable ordering of a good type which can be found out in reasonably very less amount of time, you are going to get a very good compression. The best compression finding is a very difficult problem, but like from 98% compression to 97% compression or 95% compression, I am very happy. But I do not want to go from 95% to 97% compression by spending hours and days to find out that best ordering. That nobody does. But for typically most of the orderings, you are going to have a very good compression. That is one good thing. And there are some other issues, like there can be inconsistent paths if there is no ordering. Ordered BDD is also called reduced order BDD. That means, what do you mean by inconsistency here? Because say that I want to find out whether two binary addition diagrams or two functions are equivalent or not. If the same binary ordering is taken, then basically there will be two identical ROBDDs for these functions. But if the orderings are different, then you will not be able to do the comparison, because the orderings will look different. So that is why they are saying that for most of the meaningful comparison, we always have to order the variables for a given example or a given context. For every case, the ordering has to be maintained. So therefore, you always use the term called ROBDD. Now this is mathematical. So what do you mean by a variable ordering? So basically, let this be N1 to N be the ordered list of variables without duplications, because A, B, C, D, E, F, no variable should be duplicated. So these are all your input variables x1 to xn, and let B be a BDD of whose variables occur somewhere in the list. So there is a BDD, okay, then, and there are a lot of variables x1, x2, x3, and all of them are happening in some levels of the one, maybe x2, this may be x2, x3, this may be x5 or something like x3, That means in your binary decision diagram, all the variables are appearing at some levels. There means none of the variables are redundant. At least in one path they are there. Means the binary decision diagram, when you are drawing, it is not the case that the node x3 say is nowhere appearing in the tree. In one path it may not be there, but in other part it is there. Then the BDD has a ordering x1 to xn if x1 is the leaf node, and then x2 will be found out in the second level, x3 will be found out in the third level, and so forth. But the idea is that you may not find out x2 in all the paths from x1 in the second level. Some path from x1 may be directly going to 0 or 1. In the other part, the second level, x2 will be there. That means in at least some path, the x2 will be there in the second level. That is the difference between a binary decision diagram and a binary tree. Binary decision tree means every path you will have x2 in the second, x3 in the third level, and so forth. But here, in all the paths you may not have the respective node at that level, but in at least one path it will be there, and the ordering is fixed. That means in no path you will have x3 first and x2 second. That will not be the case. If x1, x2, x3, x4 is the ordering, so in all paths or in some path the ordering will be maintained, like x1, x2, in that part x3 may not be there, x4 and x5. But it will never be the case that there will be a path where x1, then x2, then x5 and x3, that will not be there. So this is actually the variable ordering. That is root node, then in the second level at some path there will be x2, 3 means at some path there will be x3 and so forth. Now interesting. I have taken, this is the function x1, so this is your function, x1 plus x2 dot this one is the function. I have drawn a OBDD, reduced order OBDD with the ordering x1, x2, x3, x4, x5 and x6. So x1 is there, x2 is the path. Of course you see in this path there is no x3, x4 and x5. But there is a path in which case the second level x2 is there. Similarly, in this path there is no x2 over there, x3 is directly coming. But if you look at it, there is one path where x2 is there. So there will be one, every path, there will be at least one path where all the variables are there. So there are no redundant variables. Secondly, in no path you will be able to find out that x3 appears first and x2 appears next. That is not going to be the case. If in some path x2 is appearing after x1, that means in that path x2 cannot be present. So in this tree basically the ordering is x1, x2 and x3 and x4, x5 and x6. So if you see x1, x3, x4, x5, x6 and so forth. So as it is very much compressed, in some paths some of the nodes will not be there. That is obviously the requirement when you are going from BDD to binary decision tree to binary decision diagram. So, but in no path you will find the orders flipped. So, in this case the ordering is this, and this is, if you draw the binary decision diagram, which you can take as a homework, you will find out that this is the size of the tree. Now, another binary ordering. This is just the name. I mean, I can change, I mean, this is x1, this is, I mean, this is just for this example, it happens that x1, x2, x3, x4, the serial ordering is going to give you the best, one of the very good ordering. If you take a jumbled up ordering like x1, x3, x5, x2, x4, some ordering, you will find out that the tree is almost exponential in size. So, do not go by the fact that that is this function is x1, x2, so I have taken the variable ordering in a serial fashion. So, I am getting a very good structure, and if I am taking a 1 bit flip like x1, x3, x5, x2, I am going to get a jumbled order, I mean very big size BDD. It only happens for this example. What I try to show is that for the same function, if you take different combinations of ordering, you are going to get very different size tree structures. So, this one is very compact and this one is very exponential. But this is the, in this case, this is the best ordering and this is the worst ordering. Both are very difficult to find. Any good typical ordering you will be finding that I am going to get a reasonably good compression. So, there is a standard package called CUD package, which actually implements this whole BDD algorithm, and in fact internally they have nice heuristics to determine good variable orderings, not the optimal one. So, that is what I am saying that people do not try to find out the best ordering. Finding the best ordering will actually blow up the problem exponentially, and it will again land up to the issues of binary decision tree and all those things. There are good heuristics which will find out somewhat very good variable ordering, where you will get very high compression like 99% plus or even higher. So, we always typically try to find out the good ordering, and then we are going to use BDD construction, whether by Shannon's expression. Tomorrow we will see some other ways of construction, and finally we are going to lead a very complex data structure. So, what are the applications of BDDs? That is actually, first is called expression equivalence. That is, there are two functions given, you have to find out whether they are equivalent or not. How you do it? We basically have a typical way, same variable ordering, try to find out the RO BDDs, and if the both BDDs are equivalent, same, should not be equal, I call it exactly like the image of it, then you are going to say the functions are equal. Why it will happen? Because for a given variable ordering, the RO BDD will always be same, you cannot have any further reduction. So, if I have the function A and function B and I take the same variable ordering, of course, I will have the most short minimum size tree, and of course, they have to be same. Then there is something called validity of Boolean expression. Validity means basically a function, if it is always true, then I say that the function is valid. So, in this case what is going to happen? The BDD will have no zero node. Sorry, no, there will be no zero node in the leaf, that node will be eliminated. All the paths will direct you to 1. That means for all input cases the answer is going to be a 1. So, that is actually called the validity of Boolean expressions. There is also very important in some kind of verification cases, because we want to find out by manipulating by function elimination, labeling, etc., that the output of the function should always be 1. That is, all cases it is satisfied. There is something called satisfiability, that is, at least in one path it is satisfied. Then in that case there should be a node in the leaf label marked 1. If there is the node 1 in that, that means there is some paths which are leading to 1. That means at some places the expression is satisfied. Another very important is finding out of the redundant variables. Already we have seen in the test or ATPG cases that if there are redundant circuit variables, then that fault cannot be tested, and your ATPG algorithm keeps on looping, trying to find out alternate paths to get that fault tested, but that fault is non-testable because of redundancies, and you kill lot of time in ATPG. So, if you have a Boolean function, you directly want to implement a circuit on this. If it is a very big circuit, you cannot use espresso, you cannot use Karnaugh map, etc. So, there can be any chances of redundancy happening. But if you can represent in terms of BDD, if there are some redundant variables, that means the variable happens nowhere in the BDD, not even in a single path. That means that function, that variable is a don't care variable, just remove it. In these examples, basically x2 is not means a redundant variable, because in one path it occurs. But for some functions, or in most of the functions, you will find out that there are some of the variables which will appear nowhere in any of the paths. That means those variables are redundant and you have to eliminate them. In that case, there are a lot of advantages, area reduction, testability becomes easy, and so forth. So, these are some of the very prominent and important use of ROBDDs, and the advantages all comes because of compression and because of ordering. Without ordering, only with compression you cannot do much, because for the same function, if you have different ordering, nothing can be compared and equivalences cannot be checked. So, once it is a reduced order, once it is reduced binary decision diagram with a variable ordering given, then the utility actually becomes a great utility, and this is actually one of the heart of data structure of all the CAD algorithms. So whenever we talk of circuits, functions, state machines, we all represent them in terms of binary decision diagrams. And again, as I told you, what we do basically, we take a typical ordering, or the tool or heuristics exist which give you good variable ordering, and you get a typical very good compression, because for most of these systems we develop, the all combinations of inputs are actually not valid, or we do not require them, and they are do not require to be modeled itself. Only a very few fraction are meaningful. So that is the key idea of going for verification of complex systems. Then instead of basically making a large size of state machine explicitly, we will try to represent everything in terms of binary decision diagrams, so that all redundancies are eliminated, and try to model all these model checking algorithms like labeling, searching, etc. in the BDD itself, which is actually called symbolic way of doing it. Next class what we will try to do, we will quickly try to see another way of doing generating the BDDs, giving a circuit itself, rather than not going for the Shannon's method. Like we have a circuit, we have the variables, then how can we quickly make a binary decision diagram out of it, which is will be done possible through operations on BDDs. Then we will also try to see some interesting advanced structures, because anyway in testing we have already seen that whatever you do, if you remain at the byte level or bit level, then nothing can be done when you have large systems like systems of systems. So in this case also we will try to move ourselves from this binary business to arithmetic business, integer business, high level abstraction. So advanced version of BDDs like arithmetic decision diagram, high level decision diagrams also we will try to see in the next lecture. But one thing, the philosophy everywhere is similar, that you have to remove the redundancies. Thank you.